So, as I mentioned earlier, the biggest problem of unifying all the forces has been gravity. So, to understand that a little bit, I'm going to talk a little bit more about what gravity does or is. And the reason it's important is because in the very, very early universe, the particles flying around are so hot, they're so energetic, that because of Einstein's equation, E equals mc squared, they essentially have a very large effective mass. Okay, so they have a very large gravitational pull. It's so high that we can't ignore it when we're studying, really, really high energy particle physics. And according to Einstein's equivalence principle, this is basically the foundation of general relativity, the theory that he formed about 20 years after special relativity, is that there's no way you can tell a difference between gravity pulling on you and an accelerated reference frame. So if I'm in a car and I'm accelerating, pulling forward, then I feel a force pulling me back, right? And Einstein said there's no way to tell the difference between that and gravity itself pulling on you. And so to explain this mathematically, he suggested that space-time itself is geometrically curved. All right. So to imagine this here, let me imagine. We can't really imagine higher dimensionality. So imagine that our world exists on a two-dimensional plane. Okay. So we can only, our universe is this sheet of paper, right? But if we were to curve it around on itself like that, we could essentially start at one point and just go forward and end up back at where we started if we just went forward in a line. Okay, that's the idea of a curved space-time. There's also weird geometry that goes on. Normally a triangle has 180 degrees in its angles, but on a curved space-time, the triangle won't necessarily have 180 degrees in all of its angles. You got them up.
I tried to draw a little diagram of space-time warping, but it came out really crappy. So just imagine that it's warped, like a warped sheet of rubber. You've probably maybe seen the diagram somewhere.
So yeah, imagine that you have like a big sheet of elastic, right? And then you can imagine the curvature of gravity by, what if you like dropped a big bowling ball on this sheet of elastic, right? It would make a depression, it would curve down. Okay, so again, our world, our universe that we live in is this two-dimensional membrane, but it's curved, and if I shot, flick the golf ball in towards it, say it's like the moon or something, it would want to fall down towards the bowling ball, right? Like a gravitational pull. But if I gave it maybe some circular motion, it could actually get in just the right motion to spin around it forever. And that's basically what the moon is doing now. It's in a gravitational pull that's circling our Earth. But let's say that instead of a bowling ball, I had the same amount of mass, but I just shrunk it down, right? So to the size of a baseball or golf ball or whatever. It's going to make more and more of a depression at that central point on the elastic membrane, right? And if I get enough mass concentrated into enough of a small area, it's going to make such a deep depression, it's going to actually tear the fabric. Okay? And that's basically what is called a singularity, and it's also the essence of what a black hole is. Okay? A black hole is essentially a tear in the fabric of space-time. It's so curved that nothing can come out of it. No matter what I flick in, it's all going to just fall through, and nothing's going to be able to come back out. Not even light, right? And light is the fastest that anything can travel, so if light can't escape, then nothing can. And inside of these black holes, there's some really weird physics going on. Basically, near the event horizon, which is sort of the outer shell of which nothing can, it's a point of no return. If something goes in, nothing can come back. Gravity itself has an effect of time dilation, and this is actually a measured, this has been measured in experiments, that if you're near a high gravitational field, that gravitational field is actually going to slow down time. So they did an experiment where they flew a plane like 6,000 meters in the air or something like that, had two synchronized watches, and they found that the one on Earth actually went slower by a very small amount, but it was significant and measured. So near gravity, if we send, say, an astronaut in towards a black hole, then what we would see is, because because the time is essentially slowing down near the black hole, that we wouldn't ever actually see the astronaut go in. It would take an infinite amount of time for him to actually fall in. But if we were the astronaut itself and looked out at the universe, we would basically see an infinite amount of time passing on the outside world. We'd see civilizations rise and fall. We'd see the sun swallow the Earth and the solar system and everything fall into other black holes and stuff like that. But to the person falling into the black hole, we'd just fall right in and wouldn't feel anything weird. Until we got inside the black hole, in which case there's a lot of weird effects. Basically, time and distance switch meanings. So if I was to follow the flow of time, I would be like stepping to the right or stepping to the left. And oppositely, if I was to move left or right, it would be like I was aging. And if we were to keep going into the singularity at the center, we could actually theoretically reach something called a wormhole. And what a wormhole is, our space-time is curved like this. Sorry.
It was a little rough getting these posters here to Burning Man. They got a little tore up.
So imagine I go into a singularity right here. I could basically tunnel through here instead of having to travel all the way around space to get to a point down below. So I could theoretically either just warp somewhere or could even time travel, go back or forward in time. Yeah, you'd probably get ripped apart if you ever went into a black hole anyways. But anyways, so the point to all of this is that at the really early universe, the energy was so high that even though gravity is weak relatively to the other forces, it becomes so strong, it has these really weird effects that we can't ignore it, and that's why it's been so hard to unify it with the other forces.